the wrong input. There we go. Okay, so today we're going to cover Chapter 14, Site-Cast Concrete. Next week we'll cover Chapter 15, so we're continuing in order for the next week. And yes, I do owe you a list of all of the stuff, but I will get it to you, I promise. Chapter 15 is precast concrete, so we'll cover that next week. And then we'll move on from there into Chapters 8 and 9, which are brick and stone. So we jump backwards then. But I'll remind you of that before we get going next week. So today's all about site-cast concrete, and the key here is that this is stuff that happens on the building site, right? Everything happens there, and we're going to talk about how do we form up the concrete, how do we make the various walls and floors and all that sort of thing. So we'll start, maybe, if we can go forward. I just replaced the battery in this. Are you really not going to work? Should. Well, we're going to go back to the old-fashioned way. Maybe not. Maybe the old-fashioned way is not even going to work. Okay, so we'll start with the ground, right? And we'll start with casting a slab on grade. And we mentioned slab on grade a couple lectures ago when we were talking about kind of base excavations and foundations. But we're going to go into it in a little bit more depth and a little bit more detail today. So the point of a slab on grade is it's basically what's directly below your feet right now, right? It's a concrete floor to a building. It tends to be the cheapest kind of foundation that you can make, right? Because it doesn't involve a lot of form work, right? And it lies directly on the ground. Okay, we're going to use it for things like roads, right? If you go on a lot of the freeways, they're a slab on grade. Sidewalks are almost always slab on grade. Your back patio, if it's concrete, chances are it's a slab on grade. Airport runways, good example, right? Ground floors of buildings, obviously you're not going to have a slab on grade if it's a second story, right? It has to be on the ground, that's the point. But it's a pretty inexpensive building method, primarily because it experiences almost entirely compression, right? It's not spanning anything. If you stand on this slab, right, or you sit on this slab right now, all of your weight is going directly down onto the concrete, and all of that weight is traveling through the concrete and onto the ground that's below, right? So it's not really spanning anything. It doesn't involve a lot of complicated structural pieces. It's relatively simple, okay? No surprise, we use it very frequently on job sites, certainly in the state of California. So how would we go about creating a slab on grade in the first place? Okay, so you walk to a site and you want to build a slab on grade. Obviously, in Chapter 1, we talked about building permits and zoning and all that stuff. So we're assuming that we're okay to build, we have permission to build, right? We have the engineer's drawings and that sort of thing. But how do we go about building a slab on grade? Okay, so the first thing that we know is that if we're going to put down a slab on grade, we have to get rid of any of that organic topsoil, that good stuff that your plants grow in the backyard. We've got to scrape that stuff away because it's not a suitable bearing surface for that slab. Okay, so we're going to scrape that away, right? And chances are, depending on how high or low your building is, you may need to do a little bit of an excavation and get rid of some of the dirt that's existing on site, right? And most of that is excavated out so that you have room for these other things. Okay, and so below a slab, we're going to have 4 inches or more, and this is going to be dependent on whatever the engineer decides is appropriate, of a 3/4 inch crushed stone, right? This is designed to be what's called a capillary break, and it's called a capillary break. And so the idea here is that if you think of crushed stone, right, providing a base rock so that you can pour your concrete on top, if you think of that as a porous surface, right, something that water could go through from the top, right? The same happens from below, right? If we had the dirt right up against the bottom of the slab, right, the dirt would pull the water up to the surface and put water directly in contact with the slab, okay? If we instead have that rock layer underneath, which is what you have, right, if the dirt starts to swell and the water gets in there, right, it doesn't have any place to collect, right? It can drip out again, right, and not come in contact with the slab. So there's no way for the ground to wick moisture up into your building. And this can be a big problem if you have a slab on grade and you have poor drainage around your building. I had a project that I worked on. It was in Rossmar, and all the buildings out there are slab on grade. They're very, very plain in their construction, very cheap. It was a slab on grade, and it was kind of down this slight hill in a depression. And my particular unit that I was working on was against the hillside. And so this was a slab on grade. It had been done in the 60s. They did have the crushed stone. They had the capillary break. It was good, but their membrane, which we'll talk about in a second, had some holes in it. Right? And when I pulled up the carpet and got rid of the old floor and whatever, there were signs that moisture had come through the slab. Right? And so this is the problem. If you don't do this stuff right, you can get moisture inside your house. Right? And that's the big risk in a slab on grade, is that the moisture could come. Certainly, if you have a crack in the floor, the moisture could come right through that crack. And it's something you have to be really careful of. Right? Now, of course, there's mitigating ways of dealing with it. So I ended up coating the floors with this epoxy resin that seals off the top of the concrete so that you can then put carpet down and it won't come through. It's actually this really weird stuff. It comes in a 5-gallon bucket. It's expensive, but it's like the color of Pepto-Bismol pink, and it you kind of slop it on the floor, and it's this kind of thick. It's like if you ever played with like that when you mix cornstarch and water as a kid, and it's like that oobleck, Dr. Seuss stuff. You remember that from science class maybe back in the day? Random thing. But it's about that consistency. Anyway, you spread it on the floor, and it's epoxy, and when it binds together, it turns bright red instead of the pink, so you know it's cured. Anyway, this is a total long side note of a story, but the point is that if you pay attention to this stuff and do it correctly, you won't need to do that on the surface of your concrete, right? So you need this 4 inches or more, right, of 3/4 inch crushed stone as a capillary break, right? That's compacted over your existing soil, right? And that's basically a drainage layer that's going to get the water away from your slab, not let it come up through your slab, right? And so if we were to drill through this slab, we would find that below us, okay? If this, in terms of preparing to pour a concrete, right, if the slab is not between surrounding walls, okay? So if we're doing it where we have an open field, we haven't built any walls yet, and we're going to pour a slab, what we're going to do is we're going to use what's called a simple edge form, right? And the idea behind a simple edge form is it's simple, and it's a form that goes all the way around the edge of the slab, okay? It's usually built with some kind of dimension lumber, right? And we'll talk about that when we get to the wood class. But in this particular example, it's a 2x12, right? And so the idea is that goes all the way around the outside of your slab, right? And it's going to be coated with some kind of a form release agent, right? So that when you pull off that form, it'll actually release off the concrete, right? And there's going to be a bunch of stakes that go in to hold it in place. Because remember, if you put concrete on one side, it's going to want to bulge out the forms. So you need those stakes to hold it in place. But it's relatively simple. If we look at this picture right now, you could tell that they've scraped away the topsoil, right? So there's nothing organic about it, right? And they've dug down a bit, not too much, right? And so inside of this simple edge form, they'll put that crushed stone as their capillary break, and then they'll move on from there, okay? If, however, you already have existing walls and you're going to pour a slab inside, so say you had like a warehouse or something like that, you might be doing a method where you built the walls first and you're going to then pour a slab inside. If that's the case, right, there needs to be a special joint along the edge of the wall and the slab itself, right? And so this little compressive joint material just allows the slab on the inside of the building to move independently from the walls, right? So it's not going to expand and contract, right, and buckle one of the walls out. And we'll talk about this kind of isolation joint in a little bit, right, again. So this is an example of an isolation joint there. Usually it's at the edges of buildings if you have a slab that was poured after the walls of the building were erected, okay? So the top of the edge of the form obviously has to be very carefully leveled, right? You don't want to put your forms in haphazard, right, and have a sloping floor, right, unless there is an intent to have a sloping floor. So, for example, if you've been in your garage, chances are your garage, if you have a garage, has a slab, all right, or is a slab, and chances are it slopes slightly from the front of the garage to the back of the garage, right, or back of the garage to the front of the garage, depending on which way you're thinking about it, right? The idea is it slopes toward the door. So if you drive, it's raining, you drive your car into the garage, it drips on the ground, that water will drip out as opposed to back in further toward your house, okay? So it's important to carefully level that top edge, right? The slab thickness is going to vary somewhere between 3 inches for residential. Now the common is more 4 inches, but that's going to depend on your engineer. all the way to 8 inches, right? That's an industrial, like a warehouse, that kind of thing. It might be 1 foot or more for an airport runway, right? And so an airport runway doesn't have a lot of load continuously on it, right? But if you think about a big 747 coming in, right, it has a lot of weight in one point, right, when it first lands. There's a lot of force. So you need that extra thickness to help, right, absorb that force, right? If we're doing an interior floor slab, so if we were back to pouring this slab inside this room, right, on top of that capillary break, right, we'd put in a moisture barrier, right? And the moisture barrier could be something as simple as a thick plastic, right? And it could be something slightly more advanced than that, and I'll show you that in a second. As we develop newer materials, we're substituting in, right? If it's the thick plastic, right, something that looks like this, on top of that thick plastic, we will then pour another layer of crushed stone, right? Usually it's like pea gravel or something, 1/4 inch sized, right? 1/4 inch to 1/2 inch sized, right? And what that does is it will protect that moisture barrier from getting little tears in it, right? Because if you put the moisture barrier down and then it gets all cut up, it's not doing its job. You need that moisture barrier to be a nice continuous sheet. So if I'm out here working on this surface, tying off the steel, putting the little dobies in, right, the chairs to hold this up, putting my plumbing in, whatever it is, I'm not going to end up accidentally cutting this, right? And in that example that I shared about Rossmore, that's what had happened. There were a few cuts and nicks and stuff that had happened in that layer, and that was allowing the water to come up through the floor. So it can be a big deal, right? And certainly something you want to think about carefully, right? And so the other thing that it does is it provides a little layer for any water that comes in with the concrete, right, to be absorbed, right? So there's a little space for that water to go if it needs to go anywhere, right? Again, most of the water is used up in the process of hydration, right, that crystallization that happens, right, the chemical process. However, there's always a little bit left over, right? That's what we're talking about, the pea gravel, right, or sand on top of that moisture barrier, right? It also absorbs excess water during the curing process, right? If we move into the newer, stronger materials, right, DuPont's great for making new building materials that we can use, right? If we move into some of those, we may be able to get away with not having that layer, right? And so you can see something like this, for example, is a little bit more advanced material. We're using that, right, as our moisture barrier, and we're leaving it alone, right? A little bit thicker, self-healing type material, okay? But this is another example. So similar thing we're talking about here. We have a simple edge form that runs here. We've got our stakes. Notice there's a vertical stake, but there's also a diagonal stake, right, so that this doesn't bow out when you put the concrete in, right? And then on top of here, we talked about this last week a little bit. This is the welded wire reinforcing, right? It's the roll of wire, so we don't actually have to tie individual pieces. And then we have the little chairs, right, that are holding that up off the ground, okay? So here's another example where we can see that welded wire reinforcing. And you can see that it would be an awful lot cheaper and easier labor-wise to lay that out rather than to tie every single one of those pieces of rebar together, right? Usually it's available in a variety of gauges, so the wire can be thicker. It's not as thick as rebar, but usually for a typical slab, it's enough, okay? And the truth is that this is going a little bit further than what you guys know right now, but most new slabs that are built in the state of California today are not simple slabs like this. They're almost always post-tension slabs. And if you have a house that's, say, like out in Brentwood or Antioch or one of the new developments that's been built in the last 5 to 10 years, if you look in the garage of your house, there'll be a stamp on the floor saying, "Don't drill in this concrete," right? It's like stamped right on the floor of the garage. So if any of you have these houses, go look, right? It'll be stamped all over by the door, by every edge of the concrete and whatever. That's an indicator that this slab has been post-tension, because if you were to drill in it and hit one of the cables, right, it would shoot out one side. It's big problems. So anyway, we'll talk about this in more detail down the road when we get to that part of it. But the point is, slabs in the state of California are getting more advanced than something this simple. So this reinforcing would work great in the Midwest, where you don't have earthquakes and you don't have the forces that we have to deal with. The truth is, today we're going to use more of this, more of the post-tensioning and what have you in a slab to avoid the things like this crack that runs right along here, right? And there's a crack over there. There's a crack right below you. That kind of stuff happens on a traditional slab like this because of all the movement, right, and the earthquakes and that sort of thing. it doesn't prevent it from cracking. So if you had a major earthquake, right, and it caused the floor of the building to separate or crack, right, that would open back up. Now it is somewhat elastic, so if it was a very small crack, it would probably stretch over the small crack. But if it was a big crack like the one up here or the one in there, right, that kind of a crack wouldn't seal up, right? Now I could pull up the floor, reseal it, right, and it would be okay again. But that's something that you're subject to. So if you're doing it not in the state of California, this is kind of the common way. The thing about the book is a generalization, right? It's not specific to the state of California, so there's always going to be exceptions because we're here and because we have stricter requirements than elsewhere. But it's important to understand that this is kind of the basic level slab, right? If you were going to pour a slab in your backyard, this would probably be sufficient, right? You just run the risk of having it crack on its surface, okay? So in terms of actually pouring the concrete and getting the concrete into its formwork, right? We remember from last lecture, we want to place it as close to its final resting place as possible, right? Because the more distance it travels, the more likely it is to separate out, and we lose the mix of aggregates and that sort of thing. So it can be done with a truck and chute. So if you can get the concrete truck close enough to your site, you can use the chute to get it to its final resting place. Oftentimes, if you're pouring a particular slab somewhere, the distance is too far for just the chute to reach, right? So you'll end up having a pump truck come, right, or some kind of a crane and pump combo truck. And the idea there is it works just like, you know, a water truck would, where you fill one end with concrete and the pump pumps the concrete out the other end of a hose. Okay. In this particular example here, this is a hose, right? Somebody's holding onto this end. That's the concrete coming out through the pump. Okay. If we jump back a slide, right, they're about ready to pour. This crane here coming down, that's a concrete pump, right? It's coming in via crane, so the crane can be way back over here, right, and reach that back corner, right? So anybody ever done this before? Okay, a couple of you. It's a ton of work, wouldn't you agree? Right? If you think about concrete, right, it's full of sand, it's full of rock, right, and you have a 3 or 4 inch hose that you're hauling around that's full of concrete, right, that is surging, and because it doesn't pump like you turn on the faucet, right, and it goes, you know, consistently. A concrete hose, right, and pumper truck surges, right? So you're in there holding your hose, right, as best you can, and it's surging, and you're trying to place it where you want it, and you're kind of moving it, and it's this very grueling experience, to say the least.
Is there a size limit on the coarse aggregate when it's pumped?
There probably is. This can handle, this kind of a hose can handle up to 1.5 inches, which is kind of the standard concrete that we get. We're not going to see, like, you're not going to pour a dam that has the big 6-inch aggregates in it with something like this, right? It's going to be much bigger. So this is for the residential scale that you'd be pumping with something like this. But the idea here is that you're going to pump the concrete from the truck into the formwork as close to where its final resting place is, right? And chances are, when you're pouring it in, it's not going to be perfectly level, right? No matter how good you are at directing where that surging hose is going to go, it's not going to be perfect, right? So you need some way of getting the concrete to approximately the right level, right? So you're pushing as much concrete in as you can, right? After that, you're using things like rakes and shovels to push it from one area, right, up against a board that can help guide you, right? So you spread it with the shovels, you spread it with the rakes, right? If you're not using chairs, right, this is the thing I talked about before, you can reach through the concrete, because remember it is a slurry, and you can pull up that reinforcing, welded wire reinforcing, up into the slab so that the concrete oozes around underneath it, right? Which is acceptable, though it's not as accurate as if you had chairs, right? You know if you put the chairs in that the reinforcing is right where it should be, right, at, say, 2 inches above the bottom of the slab, right? If you just reach in and pull it up, maybe it's 3 inches, maybe it's 1 inch. You don't really know, right? But it's another method that is commonly used, okay? So after you have the concrete roughly in place, right, you're going to use a board, which is called a screed, right? And you're going to pull off the extra concrete. And chances are, when you were a little kid, you played around with this kind of stuff, or if you've ever baked, you've done the same kind of thing, right? So we use the baking example for a second, right? you need to mix out how much flour and how much sugar go in your cookies or whatever it is you're baking, right? And so you end up scooping up, right, the flour, and then you take a knife and you draw it across the surface of the flour to level it off and get it nice and flat, right? This is exactly what we do with concrete, right? They'll recognize, obviously, the concrete is full of things like rocks and whatever. It's not as fine as flour, right? But the idea here is that you fill in the excess concrete, and hopefully you have a board that's long enough or wide enough to span between one form and another form, okay? And this is a better picture of it, right? So you have a board here, right? And it spans across to the other formwork on the other side, and you have 2 or more people working on it. And what you do is you work with like a sawing motion, right? And you slowly move forward and you push the excess concrete, which would be on the back side of this, right, back into the area that doesn't have the concrete in it, right? And so that gets it roughly level. You got a question? Exactly. So as soon as you get the concrete into place, you're going to start this screeding process, right? And so the idea is that as you're doing it, and you can see it right here, right? As we're pouring concrete here, someone else is working on the screeding to move it there. So concrete is a lot about timing, right? And the people that have done concrete know this, and certainly the people who do it professionally are very good at this, getting the timing right, because you have to do things in certain orders so that it works smoothly, right? So if you've never worked with concrete before, when you pour your concrete beam, you will suddenly learn how important timing is, right? Did I get it in at the right time? Is it starting to cure too fast? That kind of thing, right? So anyway, screeding happens. You're moving this board back and forth in a sawing motion. You keep a little bit of excess concrete right against the board, right, so that it fills in any holes that you might have, right? If you end up with a hole, you move back, you put more concrete in, and you keep working it, right? And ultimately, you end up with, right, a slab, right, that starts to be more smooth, right? This is an unconventional pour, so they're using a smaller board to try to work with it. It's a little bit harder to do it that way, right? So this seems to make sense if you were in a residential scale. If you were, however, in a large building like this one, or say an airport hangar or something that was a slab on grade, right, you'd use something more like this, right? And so this is a power laser level screeder, right? And the nice thing about something like this, because it's operated based on the lasers and can adjust for level, you can also plug in a certain grade, right? So you can have slope that's adjusted for in something like this. So if you're doing a really large scale pour, you still need to get this roughly smooth, right, so that it's in its correct placement. So this would be almost impossible to do by hand, because how would you know where it was too high, where it was too low, that kind of thing, right? So you use something like this. It's a machine. It will do the screeding for you, right? Obviously, in the back, we see the rebar, right, not covered completely by concrete, and they're working their way out from here. Make sense? Right? Much larger scale. Okay? After you've screeded the slab, so after it's roughly level, right, you're going to do the first step, which would be an initial floating, right? And it's completed using a flat surface tool that's somewhere between 4 feet and 10 inch, 4 feet to 10 feet in length, right? I was being thrown off because I had in. I thought it was inches for some reason, and that was confusing. No, 4 feet to 10 feet in length, right? These are called bull floats. So you can see an example here, right, of the bull float. That might be a 6-foot bull float, right? And so the idea is they've already screeded off. There's a little bit left over of a screed board, right, getting that initial level. And then they're going to use a bull float to help consolidate that top layer of concrete, right? So it starts to pull a little bit of the water to the surface, right? Make sure that it's nice and compacted right at the surface, and starts to form the surface of the concrete for us, right? And it flattens the surface. It gets rid of some of the imperfections, right? Here's another example using a bull float. This is a little bit smaller, right? And he's starting to work to finish off the concrete. And you can see the difference between the rough concrete that hasn't been finished yet, or hasn't had its initial floating, right, and the concrete that has had its first set of floating, right? Notice that there are still little gaps, right? There's little things that aren't quite perfect yet. And notice also that it's incredibly hard to finish around all of the plumbing and the other things that poke up through the slab, right? So you have to be somewhat aware that your finish is never going to be quite as good around those areas, right? You can do the floating at a much smaller scale, right, with a hand float instead of, one of the big floats. Obviously, this is at a smaller scale. A little bit less accurate, a little bit more freeform, but the concept is still there, right? So a lot of times in concrete, it's worked in stages across the site, right? So it's a continuous pour, and while you'll start at one end and you'll start pouring and you'll start screeding, right? And then by the time you're pouring the other end and screeding the other end, right, someone's already doing the initial floating on the first part, right? So it's a very time-sensitive thing, right? And it's a progression. It's not something where you pour, you float, and then you move, right? You pour, you float, you move. No. You start pouring, you move the pouring all the way along. At the same time, somebody's coming back behind you and doing the floating and moving forward, right? So if you want a smoother surface, right, you're going to do an initial floating, right, periodically as the concrete is beginning to cure, right? And this is the kind of thing that really takes somebody who's done it and is experienced to know the right moment when to do it, right? Because that right moment isn't a pre-programmed thing. It's not something you can say, oh, well, 1 hour after the first float, I have to do the second float, right? It's entirely dependent on the humidity, the temperature, right? The speed the concrete's set to cure, what kind of accelerants or decelerants are in it, does it have fly ash in it, right? What's the mixture? All these variables happen, and so a good concrete worker is going to know when the right moment is to do the next floating, right? They just kind of intuitively know, they've seen it enough to know what to do, right? It can always be done by hand or with power tools. There's power floaters too, and like I said, experience is really critical in terms of doing this, right? So we have the bull float, the hand bull float that looks something like this. They do have a power float that's very similar to something like this. Harder to do initially with the power. Usually they do a bull float first, followed by a power float a little bit later in the process because this is heavier and you've got to get out on the surface to do it. But if you think about trying to do an airplane hangar, for example, that's a lot of concrete to finish, right? So you need some kind of power to help you in the process, right? So we start with a screed, followed by a float, followed by a second float, right? And finally, if we want really nice finished concrete, we're going to trowel the concrete, right? And this can be done by hand or, again, by a rotary trowel, right? And it's done after the final floating, right? So typically it's screed, float, float, trowel, right? Sometimes there's a third float in there, right? So it's going to vary a little bit. And the trowel is really the nice finish. The other thing that you could do, and I think I have a slide in a second, you've probably seen this in a parking garage, is they can do a stiff broom finish, right, where it has like a swirl pattern to it, has a little bit of texture to it, so that it's not too slippery when it's wet, right? Same thing if you're outside on concrete walkway or something like that. You don't want it to be perfectly smooth, right? They might put a little bit of extra water on the surface to expose the aggregate in the concrete to give it a little bit of texture. They might rub it with the broom. It's going to vary, right? So this is another example of power troweling. Sometimes I throw up slides that are everything not to do. So this is a good example of that. We've got the guy who has absolutely no safety protection on whatsoever. He's holding on to the machine that's working with one hand, right? He's doing a really fantastic job. Furthermore, he's also standing on the concrete with just his shoes, right? And if you're standing on the concrete with just your shoes, right, you can see he's leaving behind footprints, right, which is exactly what you don't want to have happen on the surface of the concrete, right? So you need some way of spreading out your weight, right? And so they use something called knee boards if you need to get out on the concrete and kneel, right? And typically they'll move all the way out to the center, and then they'll work backwards from the center so they can cover up any scratches or imperfections that they make along the way. But the purpose of something like this, right, is that you're spreading out your weight across a larger surface area, right? And so the concrete, as it's curing, can support, right, your weight if it's spread out. But if you do a point load, it's still going to depress, right? If you've ever worked with concrete, like when you were a little kid and you wrote your name in it or something like that, right, you know that as it's curing, you have a little bit of time when you can still do that. And that's because it's a point. But if you were to spread out your weight, right, on a larger surface area, you can actually get out on the concrete and work on it, right? So if you'd rather do a broom finish or something like that, this would be the time to do the broom finish. You go out on your knee boards, right, and you do the broom finish on the concrete, right? And so this is a pretty sweet setup, right? He's got his drink with him and everything, right? And he's out there doing his thing, right? Obviously, this is the more professional solution to it. So if we're going to cure a concrete slab, and we talked a little bit about this before, right? The slab needs to cure under damp conditions for at least a week, right? Otherwise, the surface itself may crack, right? And so if you're around a slab and you look down and there's no little fine hairline cracks, you know that they cured it like this under damp conditions. If the surface dries out too quickly, there's going to be a network of cracks that will appear just in the surface, right? And it won't look as good. So we want to make sure that we keep the slab wet, and so we can do a couple different things. We can cover it with an absorbent material like a sawdust or a dirt, something like that, right? Straw, and then keep sprinkling that straw with water, right, so that it stays wet, which obviously keeps the surface of the concrete wet. Or we can cover it with a waterproof plastic, right, which basically doesn't allow the water to evaporate, right, which keeps the water in. So you saw this slide last week, but this is a curing blanket, right? It's a plastic sheet that you put over the slab to make sure that moisture stays in there and doesn't dry it out, okay? So different methods. Obviously, if you cover it with sawdust, right, it's a bit cheaper, right, because you're just using a byproduct, especially if you're somewhere close to where there's a bunch of sawdust shavings, right? So inside a slab, there's a couple different things that will always happen. The first thing is that we have what is called a control joint. And a control joint is an intentionally weakened area, right, of the slab so that drying shrinkage can be absorbed, right? So if we had a really large slab, right, as it dries, there's a certain amount of the slab that's going to shrink and cause a crack, right? If that crack happens, right, where we don't control it, we don't know where it's going to show up, right? And it can end up being relatively ugly, right? These are intentionally grooves that are maybe a quarter inch deep to a quarter of the depth of the slab deep. The best example is right against you guys here, right? It runs along this way. There's one right under there. It runs that way, right? And the idea here is that if the slab were to crack, it should crack in that joint, right? And this is where it's a bad example because it cracked right next to the joint instead of in the joint, right? But it is what it is, right? But if you walked around the other rooms in here, you would probably find that some of the cracks have actually occurred in the joints, right? And so that's a control joint. Yeah.
Why don't they have control joints?
They do. They do. If you go on the freeway, right, and it's not an asphalt section of freeway, but if it's a concrete section of freeway, you probably notice as you drive there's a slight dun, 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 dun. Those are all the control joints that are helping it to shrink in the same place. Right? And if they did a really good job and they're nice and smooth, you might not feel them, but they are there. Right? So they can be up to a quarter of the depth of the slab. So this, right, would be a control joint. Right? That's a control joint. An isolation joint, right, or something that's called an expansion joint. Yeah. Okay, so an isolation joint or an expansion joint is always going to be a little bit wider and have a compressive material in it, right? So it has some kind of a fiber, and I don't know that there's a good one in this room that I can point to, right? But usually it's a bit wider. It's going to look more like this one, right? It goes the full depth of the slab, right, and has this compressive material that's in it, okay? In the old days, this material was a piece of wood, right? Which, if you've ever worked on an old slab, especially one that was outside, it's a total nightmare because you have this wood and it rots, and then you've got holes, and you're trying to figure out how to caulk it, and it's just a big mess, right? New stuff, we're using fiber materials, right, that don't rot, so that we can get away with that kind of thing. But the idea behind an isolation joint is it's going to separate sections of slab, right, so that that section of slab can expand and contract independently of another section of slab, right? And certainly if we were doing a parking garage or something like that where we have a really broad area, right, of slab, we need the slab to be broken down into sections so that they can move somewhat independently, right? Likewise, how many people live in an apartment building that has like a parking structure below it or some kind of multi-story parking structure, okay? The next time you go shopping and you park in downtown Walnut Creek, right, whatever it is, right, that kind of a parking structure, look around the bases of columns, right, or against walls, and chances are you'll probably see these kinds of joints, right? Remember, it has to be on the ground floor, right? But oftentimes these surround little columns, right, so that the slab moves independently from the column and doesn't cause the column to shift. Yeah. Exactly. Another good place to look at them, right? So they're always bigger usually about a 3/4 inch wide, maybe a 1/2 inch wide, something like that. They have some kind of a compressive material in them, right? And they run the full depth of the slab. So it's a separate, this piece of slab and this piece of slab, and they can move independently, right? So if we move from a slab into a wall, right? If we're going to cast a concrete wall, usually it rests on some kind of a strip footing. We talked about, right, a wall footing before. You guys remember that from last class, or 2 classes ago, right? So the footing, right, is the base of the wall all the way along, right? It's formed just like a concrete slab, right? We put that perimeter around it, and we pour the concrete, okay? Now, the difference being that instead of finishing the surface here, right, we've got a bunch of rebar that sticks up, and we're going to embed a 2x4 or similar material right in the center that's going to form what's called a keyway, right? And that key or keyway, right, I say key up here, so I guess I should say it's a key, right, relatively interchangeable, is basically it's a groove that will help to lock the wall to the footing, right? It's not going to allow the wall to slide off of the footing. It's going to lock the two together, right? And we talked a little bit about this a couple classes ago, about the challenges of having what's called a cold joint, right? A piece of concrete that's already cured, and then you're going to pour a wall on top of it, right? Or continue a column in a separate lift, right? Somebody in the back asked a question about it. I don't remember who it was, right? So the same thing happens on a footing, right? Where we poured this, right? It's cured, then we form up the wall. So we need a way of attaching these two pieces together, right? And so we do 2 things. One, we put this keyway in, right, which gives it a little bit of a concrete groove. So that's a physical thing. And the other thing is we've got all these pieces of rebar that come up through, right, the footing that are going to be tied into the wall, right? And so those 2 elements together tie the wall to the footing. Okay? So if we look at the drawn example, right, we have our footing here, right? We have our key that runs here, right? Coming up out of the footing are our dowels, right, which are just our rebar that comes up out of the footing, right? And we're going to attach the reinforcing for the wall to those pieces of rebar that are coming up out of the bottom of the footing. Okay? So take a second and draw this out in your sketchbook. It's always good to kind of practice these sorts of things. I will draw it with you as well. And when I say sketchbook, it doesn't have to be in your sketchbook, right? If you printed out the lecture pages to take notes on those, of course you can just draw on those. Do draw it separately, right? Because the act of drawing will help you remember. So even if you printed it out, right, do a separate drawing of it, right? So the idea is that we've got a wall, right? It's going to end up meeting a footing down at the bottom. If I can not completely fall over this. Right, something like this. So I would label this footing, right, and we'll call this wall, right? Remember, we're going to have a key that's put in, right? Something like that, right? So we'll call this a key. Key, right? And so we're going to have rebar that runs this way in the bottom of the footing. These little dots are indicative of rebar that's running in this direction, right? So we'll draw a few of those in. Now remember, this is not an engineering class, so if your placement isn't perfectly precise, it's not the end of the world, right? Now, we're also going to have our dowels that run in and up, right, through the wall. In this particular example, they're running up on either side of the keyway. They could run up through the center of the wall. It depends on the engineer and where he's decided to put those, or she has decided to put those, okay? So these are called dowels, so we'll label those dowels, right? On top of that, we're going to have our vertical reinforcing bars that would run here and here, right? And then we've got a variety of these little stirrups with the pieces that go this direction, right? Which is basically forming the overall cage. So I'll draw in a few more little pieces here, right, with some little stirrups. That looks something like this, right? Make sense? Right? So the act of having to draw this out helps you to understand what's happening, right? Which is why I'm asking you to draw it again, even if you printed the slides. Yes, sir. Exactly. So you would have a set of drawings from an engineer that would say this is where the rebar is going to go. So when you pour the footing, you would intentionally put those so that they match up with where the rebar in the wall would go, right? So you would do that all at once. And so if you think about the act of pouring the footing, it actually needs to be fairly precise so that these pieces come up where they're supposed to come up. Yeah. Usually you're going to embed some kind of a 2x4 or a piece of wood, right, that will then be in the concrete after you're done with the pour, right, and the concrete's been allowed to cure. You go in and remove that piece, right? And it can be fairly quick. You don't have to wait as long as you would have to wait for the bulk of the formwork. You can pull it out within 24 hours usually, and it will keep the bulk of the shape, right? Because it doesn't have to be perfect. It's not a finished piece. I had a question in the back first, and then we'll get to you. So if this is going to be the next slide, but I'm glad you asked, right? So if we needed to splice two pieces of rebar together, right, we know from the last class that they have to overlap by a certain amount, right? Anybody remember? 30 times the diameter of the rebar, right? So this overlap here needs to be 30 times the diameter of the rebar. Okay? Make sense? No. Okay, good. That's good, right? So if we had rebar that was, say, ½ inch, right? So number 4 rebar, okay? We would need to overlap two pieces of rebar if we needed to splice them together, right? So remember, we have one of these dowels that comes up out of the footing, right? We want to be able to tie it to a piece of rebar that goes into the wall, right? And we want those to be spliced together so they act as one piece. If we want that to happen, we need to multiply 30 times the diameter of the rebar, and that's going to say that we need them to overlap 15 inches. So 30 times ½ inch gives us 15 inches of overlap, right? So if we had a number 8 rebar, right, the overlap would be 30 inches, right? And so I'm not in this class going to be really specific about making you do weird calculations like that, but the fact that it's 30 times the diameter is an important number, right? It's come back up again and again, so chances are it's going to show up yet again down the road, right? Okay. So you guys totally jumped the gun on this because, of course, I'm going to ask you that question on the next slide, but it's still a good question. Okay. Did you have another question? The rebar? It's usually going to be the engineer who's going to specify it. If you're in an area where the architect chose not to hire an engineer because, and this is getting a little bit off topic into the world of architects and engineers, if you were in an area where the architect was going to stamp his own drawings and felt comfortable doing the structural calculations for it, the architect would specify where the steel would go. If it's any larger building or in the state of California or a building that somebody wouldn't want to be sued for, they're going to hire a structural engineer. So, for example, if I were doing a set of drawings, I would hire a structural engineer because I live in the state of California. And if the building falls down, I don't want to be sued. I want them to be sued, right? So that's my choice, right? But a lot of the world of architecture is going that way because we live in a litigious society where people sue each other. So given that, a lot of times it's the engineer who's actually deciding the placement. It's not up to the concrete person to decide where they go. Yeah. So it should be something that's specified by the engineer, right? Now, it might be something that's specified, we need rebar that's, 8 inches on center tied through the slab or something like that. It might be a note rather than actually drawn on a set of plans, but there will be some specific requirement for where the rebar goes. Okay? So the dowels project vertically, right, out of the slab or the footing, right, that the wall is going to be attached to, right? And they attach and overlap by 30 times. I think I covered everything on that slide, right? So next thing we have to do is we have to install the wall formwork itself, right? In some cases, the formwork may be custom for each job. Sometimes it's reused over and over again, right? Ideally, for cost savings, we're going to try to reuse this formwork as much as we can, as many times as we can, right? And so you saw a couple slides in the last lecture where there were stockpiles of old formwork that they were planning on reusing again, right? Obviously, if you have a wall that doesn't fall within a full sheet of plywood, you're going to have a cut sheet of plywood, and you might not be able to use that piece again, right? So it's always going to vary a little bit. So what we're going to start with is we're going to put forms for one side of the building on, right? The form is then going to be aligned so for vertical, so that the top, right, of the footing is braced, the top of the wall is braced, right, and it's established. Then you're going to install what are called form ties. And I'm going through this rather quickly, but on the next several slides I have actual examples of it, which will help, and I'll talk through it again, right? Then you're going to install the form ties to eventually attach the second half of the wall, okay? So let's look at this a little bit more in picture form, okay? So in this particular example, we have our footing that's already been poured, right? And so this is an interior wall in a basement. The footing goes around the outside here, okay? Then what we're going to start with is we're going to erect one side of the formwork for the wall, right? So we're picking the interior side in this example. Doesn't really matter whether it would be the interior or the outside, right? Depends on which side is easier to work with. So we put in our plywood formwork, right? To add stiffness, and I have more slides that talk about this, to add stiffness to that plywood formwork, right, we're going to add 2x4s that are on edge, right, that run vertically, and those are all called studs, right? Then we're going to add another set of 2x4s that run horizontally, and these are called wailers, right? And outside of that, see these little metal things right here and here? Those are the little brackets that will hold the form ties. Right? And that's what I was looking. I have a form tie, and I'll show you that in just a second. But that's what I was looking for, scrounging around before class, because I was looking for one of these little metal brackets, and I can't find it. Right? So let me pass out a few of these form ties because it'll help when you can actually touch these. Right? And I'm going to keep one to talk about. So here's a couple there. Right? And pass those backwards. Okay. And so I'm going to keep one to talk about as well, right? So this little thing is called a form tie. So here it is in, kind of drawn form. This is out of the book. I can use this to point too, which is good, right? Okay, so we have our formwork that's installed. These are the studs that run vertically, right? Then we have our wailers, right? And then we have this little clip that's going to tie one end of the form tie together. There it is from the outside, right? So we see the surface of the plywood, right? The form ties are sticking out, right? This is all braced on that side. There's the keyway. You can see that little piece there, right? Each one of these is form tie. You can see the rebar starting to be put in. It's not finished yet, right? Anybody recognize what that would be? Ultimately, it's a doorway, right? So we need access to this piece. Okay, so what are form ties, right? They're small diameter steel rods that hold the formwork together under the pressure of wet concrete. Okay? They're secured to the formwork panels themselves, and they remain in the concrete after it's been cured. Okay? So here's the picture example, but you have one in front of you, which I think is easier to understand. Right? So I'm going to walk through them a little bit. Right? We have a piece of formwork, and I'll pass this around in a second so you guys can see the quality of the finish on the surface of the plywood that we're going to use. Right? But the idea is that I would take this piece of plywood and I would drill a hole through it. Right? And obviously it doesn't have a hole through it, so I'm going to do it on the edge. Right? And I would install this form tie. And you can all see that there's a little nub here, right, against the interior side of this cone. So when I push this here and I push this here, right, it's a consistent distance between the outside of this cone and the outside of this cone. Right? So if I had this against the wall like this, and I had another piece of plywood on the opposite side, right, this would maintain an equal distance, right, if you imagine it on a grid pattern on the sheet of plywood, it would keep the sheets of plywood exactly the same distance apart, right? So in order to hold this, and the reason that this is so long, right, is that I have my stud running vertically, right? Then I have my wailer running horizontally, right? Then I have that little metal clip that will slide in here, and it's on a slight taper so that when I slide this in and I pound it into place, right, it'll hold this nice and tight against the formwork, which then holds the plywood panel in its correct position. That make sense? Yeah? So if we look at it here, right, this is the same thing that I'm showing, right? Here's this form tie, right, like that, right? That cone is held tight against this piece of plywood. Likewise, against this piece of plywood, we have our vertical stud, we have our horizontal wailers, and we have our metal clip on the outside that holds it a consistent distance apart. Okay? So the other thing that I want you to look at, though, right, is pull the little cone things to the end if you have one of these, right, and look very carefully right at the edge, right, of where the little nub is that holds the cone in place. You see that little indentation that's there? Right? There's a slight little groove. Right? I know it's hard for you guys that don't have them to see it. There's a little groove there. Right? The purpose of that little groove is after you take the formwork away, right, you don't want to have a concrete wall with all these metal pieces sticking out. Right? So what you do is, right, you come in here and you basically snap off the ends of these two metal pieces, which is why there's that little groove, because that's where it's going to snap. Right? Afterward, it's going to leave these little plastic cones in place, right? But you can pull those out, and then you can fill them. And I'll show you an example of that in just a second. This bottom one is just a different type of a form tie. It's virtually the same thing, right? Same concept. These are the most common ones in practice, right? So you end up with something like this that's left behind in the concrete after you've snapped the end of the form tie off, right? Obviously, you can't remove this middle section from the concrete. It stays in the concrete, right? If we look at it without that little plastic piece in it, right, we can see the cone. There's the cone depression, right? There's that little piece of metal that's left over, right, which is somewhat problematic if it got wet, right, because it's an exposed piece of metal. So how do we deal with it? Typically, they're going to plug it, right, with a little bit of grout or a little bit of concrete that's going to hide that piece, right, but also protect it from getting rust and those kinds of things inside the concrete wall. Yeah. It's usually the plastic doesn't stick to the concrete too much. Usually the reason that it stays in, if I can go back the correct way, right, is because a little bit of the concrete has kind of fallen over around it, right? If you break this out and take a piece of, pair of pliers, you can pull it out, right? So it's not too hard to get out, right? These little grooves in it make it kind of convenient for a pair of pliers to be able to reach in and yank it out. Okay? So understanding what you do about these, right? If you look at a concrete wall and you see a repeating pattern, right, on it, you now have an intuitive understanding of why that pattern exists, right, and why it shows up, right? But if you want to extend that concept a little bit, right, if you use that to your advantage, you might do something like this, right? So this is Tadao Ando in Japan. This is his Koshino house. Those of you in the architecture world have probably seen this several times already. Right? But you get to see it yet again, maybe in a different light this time, right? So what Tadao Ando did on this particular house, right, is he reduced the number of form ties that were used to hold the sheet of plywood in place. Usually it's at least 8, right, on a sheet of plywood. He reduced it to 6, okay? When he did that on the formwork, right, it allowed the formwork to billow just slightly. So when you put the concrete inside, right, the formwork pillows out just a little bit in between each one of these, right? And so that little bit of flex gives a little bit of extra texture to the concrete wall itself, right? And in this particular example, this was designed as an exposed concrete wall. So he was thinking about how the building was going to be made and using that to his own advantage, right, in how he's exposing the wall. Now, he's done a few other tricky things, right? Architects love to do this kind of stuff, where he's bringing in a light from above that's running along the length of this wall, which is really highlighting the fact that it has these little pillows in it, right? If you didn't have that there, you wouldn't be seeing that texture as much, right? So certainly there are other tricks that are being involved, but this is kind of a characteristic of his houses and the types of things that he likes to do, right? And so I show you this as an example because you need the understanding of how the building was made in order, as an architect, to make this decision, right, to do it or not do it. Maybe you want a perfectly flat wall, and if that's the case, you might use more of these form ties to make sure it's perfectly flat, right? So another example here where we're really seeing that effect. Okay, so this is continuing on that list, right? Once the ties are in place, the other side of the wall is installed, right? Obviously, after you spread the form release compound and you put the reinforcing in and that sort of thing, right? Then you're going to put the studs or the vertical braces in, right? Followed by the whalers, which are the horizontal braces, right? And then the little steel brackets, right, to hold the form ties in place, right? And then finally, you're probably going to need some diagonal braces to stabilize the wall, right? And you saw this already on the inside of the wall. There were those diagonals, right, that help keep the wall actually plumb. you'll need them on both sides to make sure that it stays correctly, right? Afterward, you're probably going to use some kind of a transit or a laser leveling device to make sure that wall is perfect on top, right? Because it doesn't do you any good to have a sloping wall and then have to build your house on top of it that's sloping and correct for it, right? If you can fix it the first time, that's always better. Yes, sir. Of a wall, it's usually dependent on the quality of the formwork, right? It's usually no more than 1 story, right? Which causes you then to have to do a second lift, right? The problem is if you extend into, maybe you could get away with 1.5 stories if you had really good formwork, right? But it starts to get really risky, even at a full story, because if you don't have good formwork that's well sealed at the bottom, the amount of pressure that's coming down, the liquid pressure from the concrete, will cause the bottom of the foundation or the bottom of the formwork to want to bust out, right? And obviously, if you're in the middle of the pour and you have wet concrete that's starting to cure and the bottom of your formwork blows out, right, all the concrete comes out and it's a giant mess, right? Furthermore, the concrete's now in contact with the dirt, right, which is mixing into the concrete, which lowers the strength of the concrete. Basically, it's a big problem, right? So you really want to be careful about how high you're trying to pour in one wall and make sure that the formwork can withstand it, right? And so generally, 1 story is about the max that people try to do, okay? So after you've leveled the top of the wall, right, you can then begin pouring. So we continue on with the same set of pictures here, right? This was the piece that we were showing before, but it works the same way out on this side, right, where we have the wall that's been placed, the one side of the wall. These are those diagonal braces. We have our studs. We have our wailers running across. We have the little metal brackets that are holding the form ties in place, right? This is the opposite side of the form tie, right? It's extending out, right? It's extending out like this, okay? There's holes drilled in our formwork, right? That formwork slides onto, right, these little pieces. We follow that with our studs, right, our wailers, and finally the little metal bracket to hold it in place. Okay? So we're getting there. We're almost completely formed up, right? You see there's all our studs. These are our wailers running across. They have a nice working platform, which is good, right? And we have all our diagonal braces. We've done our leveling, right, to get it in its proper position. We have a few other things that are happening, probably holding little anchor bolts and hold downs and that kind of stuff. Not necessary for right now, right? Notice that they have these little ties that are running across the top to help hold the wall together, right, even at the top so it doesn't tend to bow out. They're trying to get a nice, precise pour here. Oh, this, by the way, is the back of one of those pumper trucks that I was talking about, right? So the concrete comes out of the concrete truck into the pumper, right? The pumper then pumps it through a hose to where it's going to end up, right? So here's our example. There it is right there, right? They're going to pour right up onto the top of the wall. Obviously, there's no concrete coming through yet because the guy's holding onto it with one hand, which he could not do unless he's, Arnold or something, right? So you can see right down in here, there's those form ties, right, holding the walls separate. Okay, and here it is from the outside, right? They're getting ready to pour. This is obviously a relatively small job, right? Relatively small foundation. Look at how much formwork is involved in making these walls, right? It's a lot of wood. It's a lot of work to get this ready, right? That all has to go away. It's a temporary building that you're building so that you can pour the concrete. Yes, sir. I'm sorry, what? They try very, very hard to reuse as much of the wood as possible. And so even if you're doing smaller foundations, right, chances are you will try to use, especially if your engineer will allow it. Like let's say you're building foundations for your house. You did 2x12 formwork on the outside. You'll reuse those as some of your floor joists on your ground floor or something like that. So you try to reuse as much of it as possible and not throw it away, right? But even then, there is a lifespan. So one of these sheets of plywood, right, these nice sheets of formwork, might be used 8 times, right? And then the surface just starts to deteriorate too bad, right? So I can pass that around so you can see. It's a really high-quality surface, high grade of plywood, right? Now, if you were pouring a set of walls and you weren't, let's say it was just in your house and you weren't planning on reusing the plywood, you might not spend as much money for the expensive plywood. You might use something that's a little bit lesser quality, knowing that you were going to throw it away, right? But if possible, you're going to reuse it. Certainly, a lot of this outside stuff can be reused, right? The wailers and that sort of thing. Depends on how tall the wall is in terms of how they're going to space it out. It doesn't have to be continuous. If we jump all the way back to the Tadao Ando pictures, right, you can see, right, there's a sheet of plywood, right, there's another sheet of plywood, but notice the spacing of these holes for the form ties is even, right? Now, chances are they're going to put a little bit, that's a separate type of a joint. That's a lift joint, right, where we have the lower wall followed by the upper wall, right? Anyway, when you're putting these two pieces together, right, you're going to put the verticals that run all the way through, right? So your studs aren't going to be just across one piece. They're going to run further, right? When that happens, it helps to tie them all together, right? Right, so it's just stacked. There's no tongue and groove. There's nothing fancy about it, which is why you can see where the joint is. Right? Obviously, on that particular example, he was going for the pillowing, so they're not quite as close together. If you had a denser spacing of these form ties, right, there wouldn't be as much flex in those. The joints would be much tighter seamed, right? And it would be harder to determine where those joints are. Right. So, for example, on this one, right, this is just the filler piece at the very top, right? There, below that would be a full 4x8 sheet. Okay, so they've actually gone ahead and poured, right, the concrete. This is one of those anchor bolts that's going to tie the bulk of the building to this foundation. We'll cover that in, like 2 months when we get to wood construction, which seems like a long time off, but it'll happen really fast, right? So anyway, we end up with this. We're going to strip down the formwork, right? So we just remove it backwards. We take the braces off. We take the clips off. We take the whalers off. We take the studs off. Finally, we remove the plywood sheets. Right, we're left with the little stubs of the form ties left over, and we're going to snap those off, right, and then grout in the resulting holes. Right. So you guys can all walk over to the book drop area out by the library, right, and you can see this stuff. Like if you go down by the pond that's right out there, and you walk down to kind of where they load the trucks with the books and whatever, right? All of that was formed this way, and you can very easily see the plywood sheets, right, and the little holes and that sort of thing, right? So as we move forward in the worlds of technology, people have decided that building formwork, building the whole building out of wood, pouring concrete in it, and then stripping the wood off is a bit wasteful, right? Certainly, if you can reuse the materials, that's a good thing, right? But if you can find another way of not reusing or of doing something that can permanently stay attached to the building, maybe that's something that's a little bit better. So we have these alternative formwork methods, right, that are built out of styrofoam, and I have 3 different examples of them that you guys can pass around just to kind of get an idea. And so the point is behind alternative formwork is instead of building all of this out of wood, we'll build the formwork out of styrofoam, right? And the styrofoam, after it's been built, right, will stay in place and provide insulation for the building, which is a pretty good concept, right? So you can end up building your formwork, right? These are insulated concrete forms, right? There's obviously proprietary systems, right? There's one that has styrofoam that runs all the way through. Some of them have plastic that runs all the way through. It's going to vary a bit, right? And these are going to remain in place permanently as part of the building, right? And the specifications are going to vary by the manufacturer. Now you can see on those pieces that are coming around, they have like a kind of a tongue and groove system of teeth, right, that help them to interlock together, right, and not allow the concrete to blow out through the seams, right? Because compared to the plywood formwork, these have a lot of seams in them, right, which are somewhat problematic. And so, generally speaking on these, while we were talking about with the plywood formwork being able to pour a full story in one lift, right, for something like this, we may be stuck pouring a building in 2 different lifts, right? So we might have to pour the bottom 4 feet followed by the top 4 feet, right? Because the pressure of the concrete in these walls may blow out, right? And this is going to vary depending on the manufacturer and the type of concrete used and that sort of thing, right? But it's important to understand. Make sense? Yes.
Why wouldn't you always use styrofoam just in terms of the labor saving of all the carpentry?
Couple reasons. One, you may be interested in the look of the wood, right? The other thing is that you've also, if you're doing this, right, you need to somehow treat the inner and outer surfaces. So let's use the book drop right, out by the pond as a good example, right? It's an exterior wall, right, that's providing access for them to unload the books, right? But it's going to stay exposed to the exterior. If we use something like this to form up that particular piece of wall, this would be on the outside. It would be exposed, right? They'd have to clad it with something. They'd have to maintain that cladding, right? If it's outside like that and you want the concrete exposed, right, because it's a retaining wall or something like that, if you form it up with wood and then remove the wood, the concrete is its own, yeah, typical house. These are becoming far more common because they stay in place and because they provide the insulation. The only gripe I would personally have about it is that you may be stuck pouring it in two lifts, which can cause a cold joint, which could be problematic in an earthquake zone. Right? It would be up to the engineer. But I would say these are becoming more and more popular, especially in places where insulation is of value. So back east and that sort of thing.
There's a finished product versus finished product, either the wood, conventional wood. What's the cost comparison?
You know, I don't know off the top of my head. I would imagine these are significantly cheaper. These are significantly cheaper, would be my guess. But I don't know. I've never actually purchased these for a project that I've done, so I don't have any firsthand knowledge of them and what they would cost.
The labor of setting up that wood.
Yeah, is definitely. I mean, these are, you use a little bit of spray foam adhesive and you put them together, and it seems pretty easy. So, you know, you've probably got some challenges certainly with this variety of running your rebar and tying your rebar in with it. But if you've done a concrete masonry unit block wall, it's virtually the same as doing that. You're just filling it with concrete. So, but again, I don't have any cost figures on it, so I don't have good information on that. So if we move forward into casting a column, right, it's basically the same thing as a wall, right, except that instead of being a long continuous strip, it's a single pillar, right? And so all of the principles still apply, right? The footing, right, is some kind of a column footing or a caisson cap or a pile cap or something like that, right? And your column is going to be formed up on top of that. The dowels are going to come through whatever the foundation is up into the column, right? They're going to match up with whatever the vertical bars are that run the length of the column, right? And then a cage of reinforcing steel is going to go around, right, those dowels and ultimately the vertical bars, right? And there's going to be some kind of a formwork that makes the formwork, right? And so it could be a rectangular box of plywood, right? You could build up plywood and make a column out of it, right? Which certainly most square columns are like that. It could be some kind of a cylindrical steel, right, or plastic halves that are bolted together, right? And those can have some texture on them, which can be advantageous. These two, right, primarily this one, but a little bit of this one, are reusable, right? So if you wanted to pour part of the column, slide the formwork up, pour the next part of the column, if it was a multi-story column, you could do it with either one of these, right? The last option is basically like a toilet paper tube that has wax on the inside, right? It's called a sonotube. That's the brand name for it. But basically it looks something like this. It's a giant paper towel tube or toilet paper tube, wax on the inside. You slide that over your column, right, and it provides basically the formwork for it. Pretty convenient because you can unpeel it, right, and expose the concrete after the fact, though a lot of times people just leave it, right, and it eventually degrades with water and what have you, right? Very common, very inexpensive, which is a good thing. Right? Other examples here, right, this is the rectangular wood column, right? That's a steel column that's going up. You can see the lifts as we go up, right? So in this particular example, you can establish this, right, column. As you move up, you can detach and move up, right? Same thing happened if you guys remember watching the Benicia Bridge be made, right? Obviously, that's a really large column that's coming up to support the bottom of the bridge, but it's a piece of formwork that they clamped on, right? They poured the concrete, then they moved it up, poured the concrete, moved it up, poured the concrete, right, along the way up. Same thing happens with the column. So they can end up being more decorative, right? Obviously, something like this that's cast out of either aluminum or steel is going to be a little bit fancier and certainly something that you're going to reuse over and over again. Generally speaking, if you're using steel formwork, you're going to be able to reuse it many, many more times than you would if it was wood formwork. It could be aluminum, right? If you're casting against it, it doesn't make much difference. Notice, however, if you have these flutes, right? We couldn't have this be half and half, right? We need this to be broken into quarters because you need to be able to remove, right, the quarter. So if we have something, right, if, for example, this was half, right, and we had these little pieces, that would lock the formwork into place, right? So it needs to be split here and here so we can actually remove this corner after the concrete's been poured. Yeah. Is that what? It's meant to look like a Greek column, yeah. Right. You know, obviously it's not a Greek column, but it's meant to look like it. Okay, so we have to use an architectural example. Sorry, 220ers, right? You get repeats, but yeah, I can't not use it. But also, we've gone through kind of the traditional stuff. So what happens if you break the boundaries a little bit, right? And so this is Todd's Department Store by Toyo Ito in Japan. This is a concrete structured building, right? It's kind of a hybrid between walls and columns, right? But they work kind of as both, right? So this is what the building looks like from the outside. It's primarily concrete and glass, right? But the concrete provides the primary structure for the building. I apologize because some of the slides are a little bit blurry, but it is what it is, right? You can look at them afterwards on the computer. It might be a little bit better, right? But it's this mesh, right, of concrete that in and around, right, the glass windows that are open provides this kind of an atmosphere inside the building, right? So it's a really unique building, right? But obviously a building that would be very challenging to make the formwork for, right? And so this is what it looks like from the outside. Notice, however, right, if we're looking at the outside of the building a little bit closer, right, here's our formwork, right? There's our plywood panels. There's all our little form ties. So no matter how extravagant the building gets, right, we can still make it using the same methods that we've talked about before, right? And so obviously this is, far more complicated, but I like this example because you can see how far you can extend the technology to design what it is that you want using the same stuff that you would, work on your normal house with, right? And so here's another example. You can see this a little bit better, right? Here's all of those form ties. Now, right, notice the spacing is much denser than the Koshino house, right, because he wanted this to be a nice, flat, sharp corner, sharp surface, that sort of thing, right? So another example, right? There it is from the backside. It's kind of fun how it wraps around. Nobody ever sees it from this angle, right? This is the back angle. It wraps around another building. And so this was kind of one of the original plans for how he developed, right, where those columns would go, right? These are more of the structural drawings starting to figure out where things go. This is up on the roof access. So we get to the formwork, right? So what if I show you a bunch of pretty pictures, right? We have to see the actual stuff in practice, right? And so this is a relatively large building, right, in the skyscraper. We talk about the density of steel, right, and the challenges of getting the concrete in and around the density of steel. This is a perfect example, right? So if we're looking, and I apologize that these are, again, somewhat blurry, but I'm limited in what images I have access to. So here we go, right? This is the inverse of one of those shapes, right? Notice we've got solid pieces here and here, right, that are representing the voids. That's where the windows are going to end up going, right? And look at the nest of rebar that's inside this, right? And this is not little tiny rebar, right? I would say the smallest rebar in here is probably number 6, number 7, something like that. This is big, big rebar, right? And you can see as they're building it up, right, here's another example of that formwork. This is obviously where that Y is going to go, right? These are the voids where the windows are going to go, and we're tying that formwork into place, okay? So in order to pour this concrete, right, and have it not have air gaps in and around the density of this material, they had to use that very special concrete that was called self-consolidating concrete. You guys remember that from last class, right? It has very few large aggregate pieces, right? It's mostly small aggregates. It has superplasticizers in it. It has a bunch of high-tech stuff to get the concrete to actually flow around this material, right? There's not even enough room in one of these forms to get a vibrator in to help consolidate the concrete, right? So it took a very special blend of concrete to even be able to build a building like this, right? But this is, again, the best example of kind of showing how far you can extend this to create a building that's like this, right? So for those of you architects people out there, sometimes it's fun to see more drawings of how this kind of stuff works. And we've got a variety of floor plans and what have you. So that's what the building looks like at night, right? And those joints, right, these kinds of pieces were what we were just seeing in the slide with all that rebar inside it. Okay, so we're going to take our break now. It's 8 o'clock, so come back at, it's a little before 8, so come back at 8:15, and we'll keep going. Okay?